Welcome back to the Machine Learning Mastery playlist. I am thrilled to have you join me today as we explore the enchanting realm of decision trees, a powerful algorithm that can truly transform your predictive modeling endeavors. So, get ready to unlock the secrets of decision trees and take your machine learning skills to new heights. But before we dive in, let me quickly introduce myself. I am Bhaskar, your guide on this machine learning adventure. In this video, our focus is on decision trees, the versatile algorithm that's widely used for both classification and regression tasks. Why are decision trees so important? You may wonder. Well, they offer a unique combination of power and interpretability. They allow us to make sense of complex data patterns and extract valuable insights, all while keeping the decision-making process transparent. Now, let's dive into the three main sections that will unravel the magic of decision trees. First, we will build a solid understanding on decision trees themselves. Then, we will explore their implementations. And finally, we will discuss practical tips and applications that will help you unleash the full potential of decision trees. Are you ready? Let's go. Session 1: Understanding decision trees. To begin our journey, we need to grasp the essence of decision trees. Picture a magnificent tree with its branches representing decisions and its leaves containing the outcomes. That's the essence of decision tree. So let's take a tree. It has branches which are having sub branches like this, and final will have leaves. So each branch and sub branch are decision making nodes, and each leaf is the final outcome. Within the decision trees, we encounter two main types of nodes: decision nodes and leaf nodes. Decision nodes guide us through the branches by posing questions based on the feature values, leading us to further decisions. On the other hand, leaf nodes represents the ultimate outcome or predictions. That means each branch is a decision-making node, and finally the leaf is the outcome. But how does the decision tree decides where to split? It's through a process called splitting, where the tree statistically divides the data based on the values of the feature. To determine the optimal splits, we rely on a measure called entropy and information gain, which allow us to find the most informative branches. Let's take an example. First node is the root node, and we're having branches, decision node, and which is having further decision node, and the process recursively continues, and at the end we're having leaves or leaf node. This is our outcome. That means if you have a node, humidity, just before leaf node, it has two values, normal or high. This is our final outcome, and this is a decision node. So this is what a decision tree is. But how does a decision tree decide where to split? It's a process called splitting, where the tree statistically divides the data based on the values of the feature. To determine the optimal splits, we rely on methods like entropy and information gain, which allow us to find the most informative branches. Now, imagine recursively building a decision tree where we continuously find the best split at each node. This recursive process creates a robust and powerful predictive model. In data science, entropy is a measure of impurity or uncertainty in the dataset. Entropy quantifies the disorder or randomness in the distribution of classes or categories within a dataset. Entropy ranges from 0 to 1, 0 representing perfectly pure dataset. That means all examples belongs to the same class. That means if we have 10 data points, all 10 data points either positive or all 10 data points either negative. That's what perfect classification represents. Whereas in the case of entropy equal to 1, if you have 10 data points, we have 5 data points as positive and 5 data points as negative class. This is what entropy 1 represents. Mathematically, the entropy of a data set with respect to target variable is calculated using the formula entropy equal to minus sigma p log p minus sigma p log p. That is the entropy of data set, where E is our entropy, is the summation, and P is the proportion of instances belonging to a class in the data set. When splitting a data set based on an attribute, the entropy is calculated for each possible value of an attribute. The weighted average of entropy after the split is then calculated to determine the information gain. So, to determine the information gain, we're calculating the weighted average of the entropies. The attribute that yields the highest information gain is selected as the best attribute for the split. In simple terms, entropy measures the amount of uncertainty or randomness in the dataset. It helps decision tree algorithms to find the most informative features or attributes for splitting the data, leading to the creation of more accurate and robust decision trees. Information gain is the expected reduction in entropy caused by the partitioning examples on an attribute. That means what is the decrease in entropy if I make a split? If we have a node, if we make a split, we are splitting. If I make a split, how much entropy is reducing? That means, so to make a decision, we are having features, right? Each feature is a variable. So if we have 5 features, 1, 2, 3, 4, 5, out of 5 features, which feature at what value we are getting the maximum decrease in entropy, that will be our feature and particular split. So let's take an example. Assume we have a node humidity, right? Previous example. It can be either normal or high. Assume its entropy is 0.9 and 6 positive and 1 negative. And for normal is 3 positive and 4 negative. That means 3 data points are positive and 4 data points are negative. Similar here, 6 data points are positive and 1 data point is negative. So what will be our entropy? Entropy is equal to minus sigma p log p. So this will be our gain. Gain is 0.9 minus 7 by 14. Its value will be 0.98 minus 7 by 14 into 0.59. And the final value will be our gain. So if you see the example which we have taken, humidity is split into two. One is high and other is normal. And here we are having 3 positive, 4 negative. Similarly for normal, 6 positive, 1 negative. If you sum this, it will be 7 data points. It will be 7 data points. Total is 14. For normal, we are having 7 by 14. And similarly for high, 7 by 14. And so the formula goes like as we have seen 0.9 into 7 by 14 into entropy of normal, which is 0.98 minus 7 by 14 into entropy of high, which is 0.59, and the final value will be our information gain, IG. I hope this is clear. So let's take a regression example. Assume you have data points 1, 2, 3, 4, 5, and 6. So how will you calculate entropy and information gain for regression points? As you have 6 data points, we need to find the split. So how will you calculate a split for regression point? First, we sort it. It is in a sorted order. Then we take the average of every two data points. That means 1 plus 2 by 2, 2 plus 3 by 2, 3 plus 4 by 2, and so on. So it will be 3 by 2 is 1.5, 2.5, 3.5, 4.5, and so on. This will be our split. So we're having 1, 2, 3, 4, 5, 6, and this will be our split. Split, these are our split points. So we take node 1. Node 1, split is 1.5. So 1. Is it greater than 1.5? No. So 1 negative. 2, 3, 4, 5, 6. This will be greater than 1.5. So 5 positive. So we converted the regression problem into classification problem. Similarly, node 2, 2.5. This will be negative, negative, and this will be positive. 2 negative and 4 positive. So 2 negative and 4 positive. This is for second split. So like that, we will do for all the splits and taking the best split where the entropy is minimum and information gain is maximum. Why is the entropy should be minimum? Because we have seen the formula, right? Entropy minus entropy of subnodes. So this is information gain. If information gain is max, then this should be minimum. This is our entropy of split. That's how we're calculating the best split. So this process is recursive. Okay, now we have completed the section 1. Let's go to the section 2, implementation of decision trees. Now that we have understood the essence of decision trees, it's time to dive into the implementation. So there are different kinds of decision trees such as ID3, C4.5, CART. So CART is basically we are using most of the times classification and regression trees. During the implementation, one crucial step is selecting the best attribute for the splitting. We assess the attributes based on entropy or Gini index, aiming to find the attribute that provides the most informative splits. But hold on, we must ensure that our decision trees doesn't overfit the data. That's where pruning comes into the picture. So we're having two kinds of pruning. One is pre-pruning and other is post-pruning. What is pruning? Pruning is a technique used to prevent the overfitting and improve the generalization ability of the model. Pruning involves reducing the complexity of a decision tree by removing or merging nodes. So let's take about pre-pruning. Pre-pruning, also known as early stopping, involves stopping the growth of a decision tree before it becomes fully expanded. This is done by setting stopping conditions or constraints during the tree construction process. Pre-pruning involves techniques like maximum depth, minimum sample leaf node, minimum impurity decrease, and so on. So in case of maximum depth, we are setting a maximum depth of the tree. That means after a certain depth, assume this is a level 0, this is level 1, level 2. If I set a maximum depth as 2, that means we are stopping the tree at here. That's what maximum depth represents. Next is minimum samples per leaf. So let's take the same example, root node, we're having subtrees, and let's take example 3 positive, 4 negative. We're having 7 points and 3 positive and 4 negative, and number of samples are 7. That means we can set a threshold. If the samples are less than a particular threshold, we stop the tree. That's what it represents. Next is minimum impurity decrease. Setting a threshold for minimum amount of information gain or impurity. That means after reaching certain impurity or information gain, we stop the tree. Pre-pruning helps prevent the decision tree from becoming overly complex and overfitting the training data. By stopping the growth early, it can improve the generalizability of the model and reduce the chances of memorizing noise or outliers in the training data. Next is post-pruning. Post-pruning, also known as backward pruning or error-based pruning. It involves going the decision tree to its fullest extent and then selectively removing the nodes that do not contribute significantly. That means we grow a tree to complete to a perfect classification, and then once it reaches a perfect classification, we prune it backwards. So there are different kind of techniques. One technique is error based pruning or reduced error pruning. That means starting from the decision tree, each subtree is replaced with a leaf node. If removing the subtree does not significantly increase the error rate on a validation set. So what does it mean? We have a root node and we have a subtree. Okay. So what I will do is this is subtree, right? This is a leaf node. I will replace this subtree with whatever, for example, 3 positive and 4 negative. Assume at this point there are 3 positive and 4 negative. So that means maximum negative we are having. Yes, 4 negative. That means I will replace this node with like this. It will be leaf node negative. So this will be our tree, right? So we are replacing subtree with a leaf node, and this will in turn reduce our error. That is what reduce error pruning means. Next is cost complexity pruning or alpha pruning. Assigning a cost or complexity value to each subnode based on the model's performance and complexity. Pruning decisions are made by comparing the cost of pruning a subtree with the cost of keeping it. So, what is the cost of pruning a subtree and what is the cost? Based upon that, we'll prune it. Post pruning helps simplify the decision tree by removing unnecessary branches and nodes that may be specific to training data and does not generalize well to unseen data. Both pre-pruning and post-pruning techniques are used to optimize decision trees and strike a balance between overfitting and underfitting. The choice between them depends on specific dataset, available resources, and desired trade-off between model complexity and performance. Another exciting aspect of decision trees is their ability to reveal feature importance. By examining the structure of the tree, we can identify the most influential features it can have. So, in simple terms, feature importance is the average distance of a node from the root. Let's take a tree. This is the root, and you're having branches. A feature can be repeated multiple times. Assume feature 1 is repeated here, here, and here. So level 1, level 2, level 3, level 4. So it will be level 1 plus 4 plus 3 by 3. What is the average? This is for feature 1. Similarly, we'll calculate the average distance of feature 2. So it will be like feature 1 average is 2.5. Let's assume feature 2 average distance is 3.4, feature 3 1.8. So what is our order of importance of features? So whatever is the least distance, it will be most important. That means feature 3 important than feature 1 important than feature 2. This is the order of importance of features. Okay. So with this, we will move on to the section 3, practical tips and applications of decision trees. Now that we are equipped with the essentials, let's dive into the practical tips and real-world applications that harness the power of decision trees. When working with decision trees, it's essential to know how to handle missing values and categorical values. These practical tips ensures that our models are robust and accurate, and even when faced with the imperfect data, handling missing values in decision trees. So there are few approaches to handle them. One is treat missing value as a separate category. So if you have any missing value, null or none or nan, not a number, replace them with a category. Create a new category and replace them. That's one technique. Second technique is imputation. So replace missing values either with mean, median, mode, or some if you have a regression data, some regression technique. So that is one approach, imputation. Next is ignore missing values. Simply remove it from our model. These are the three techniques for missing values. Next is handling categorical variables in decision trees. So there are different techniques to handle categorical variables. As you know, we need only numbers for our models to work. We don't need any characters or strings. So if there are any characters or strings, we need to convert them into numbers. One technique is one-hot encoding. A, B, C. I replace them with columns A, B, and C. These are our rows. If A is present in row 1, it will be 1. If not 0, row 3 A is present 1. Row 4 A is not present 0. Similarly, for row 1 B is not present 0, not present 0, present 1, present 1. This is what one hot encoding is. So convert them into individual columns. Okay. So we're converting them into binary variables. Next is label encoding. That means if you have A, B, and C, simply convert it to 1, 2, and 3 numbers. Convert the characters into numbers. That's what label encoding does. But here's a catch. Be cautious with this approach. Yes, label encoding may introduce an unintended ordinal relationship. That means, yes, you know, right? 1, 2, 3. 1 is less than 2, less than 3. The relationship might be captured. So be careful. Next is ordinal encoding. If you have different categories and if you know there is a relationship between them, that means let's take it as high, medium, low. High is more, medium is less, and less, low is much less. So there is a relationship. So we can keep it as high as 3, medium as 2, low as 1. Just impute them. So the relationship is also captured. Okay. Remember that the choice of missing values and category values depends on specific data sets, the nature of missingness of categories, and decision tree algorithm you are using. It's always recommended to pre-process the data carefully and evaluate the impact of different strategies on the model performance. But decision tree offer more than predictions. They offer insights. Understanding how to interpret the decision tree allows us to extract valuable knowledge about our data, empowering us to make informed decisions. Let's explore the realm of real-world applications. Whether it's predicting the customer churn or assessing the credit risk, decision trees have proven their worth in various domains. Their versatility and interpretability makes them invaluable tools for decision making. However, it's important to acknowledge that decision trees, like any other algorithm, have their strengths and limitations. They excel in interpretability and handling nonlinear relationships, but they can be sensitive to outliers and prone to overfitting. So let's discuss about the strengths of decision trees. Strength 12. It's easy to understand and interpretable. So we can easily understand and we can easily interpret. It's direct. Next, handle both categorical and numerical data. So we have seen how to handle the categorical data previously. So they can also handle numerical data. Next, nonlinear relationships. Decision trees can compute non-linear relationship between the features and target values by recursively partitioning the data into subsets. This is our space, and we are splitting based upon a feature 1. Similarly, splitting based upon feature 2. Similarly, splitting based upon feature 3. Split based upon feature 4. If a data point belongs to this point, it's one boundary. If they are belong at this point, this is one boundary. So our space is divided into sub-boundaries and and so on. That means let's assume you are having different features. So you are having 100 features. If you have 100 features, so with these splits, our plot can be non-linear. That means why? Because this is one. We are having a lot of lines, and they can be non-linear. So distant trees can easily identify the non-linear relationships. Other advantage. They are robust to outliers. Decision trees are robust to outliers in the data. Outliers have minimum impact on splits because algorithms uses rank-based statistics rather than relying on mean or variance. So if you see in the mean or variance, we're having the mean value sigma. I mean the average value, and the average value it depends on outliers. Assume we have data points 1, 2, 3, and 4. What is the average? 1 plus 2 plus 3 plus 4 by 4. This will be our average. Assume we have another data point, some outlier, 99. What will be the average? It's much higher. Why is it happening? Because we're having outlier, and because of it, it impacts our model. But in case of decision trees, we're not taking the actual value, we're taking the ranks. Rank 1, rank 2, rank 3, rank 4, rank 5. 99 is rank 5. By taking this kind of statistical techniques, we can be robust to the outliers. Next is feature importance. As we have already seen, we can calculate the importance of the feature. Limitations of decision tree. Overfitting. Decision trees have a tendency to overfit the training data, especially when they grow deeper and complex. Overfitting occurs when tree captures noise or outliers, poor generalization to unseen data. Techniques like pruning and setting constraints can help mitigate the overfitting. As we know, if we have a tree, it can have subtrees, and it can go on till we have one sample nodes, leaf node. So if we have it, it will overfit. Why will it overfit? Let's take an example. Assume we have data points. We have data points here and here and here and here. So if you continue to go to the tree to the root node, how will the decision boundary look like? Decision boundary will look like this. So these are our decision boundaries. So we're having over complex decision boundaries. Ideally, decision boundary should be like this, but because of non-linear relationship, we're having this one, this one, this one, and this one. So that's the issue. Next is high variance. Decision trees are sensitive to small change in data. A slight modification in the training set can lead to significantly different data structures. So the variance is high. Small change in data will lead to different results. The model will change, the output will change. That's why it's high variance. Next is lack of global optimization. So decision is all about local decision boundaries, not global decision boundaries. Yes, you know, it's a greedy technique. So it will see immediate instance. So that's one issue. Next is bias towards feature with more categories. Assuming there are two feature, feature one and feature two. It has four categories and it has two categories. So it's biased towards feature one. Yes, we can tackle this by using different techniques. Instead of using information gain, we can use Gini index and some other techniques. Okay. So next limitation, difficulty capturing the linear relationships. It can easily capture the non-linear relationships, but it has a difficulty capturing the linear relationships. So that's one limitation. Congratulations on completing this thrilling journey into the world of decision trees. We covered the fundamentals, implementation strategies, practical tips, and real-world applications. Now it's time for you to take the reins and apply decision trees to your predictive modeling projects. But don't stop here. In Machine Learning Mastery playlist, you will find more advanced algorithms and techniques that will continue to expand your machine learning skills. So be sure to explore the other videos and unleash your full potential as machine learning enthusiast. If you find this video helpful and enjoyable, please give it a thumbs up and subscribe to our channel and share it with others who are passionate about machine learning. Your support keeps us motivated to create more content for you. Thank you so much for joining me on this adventure into the world of decision trees. Your time and enthusiasm mean the world to us. Keep learning, keep exploring, and keep mastering machine learning. Until the next time, thank you.